Okay, we're back with static equilibriums part two. I think we can get this done in two parts. Okay, so let's go back to that problem then. So here we were, and I should say that these torques, the lever arm and the force are always perpendicular. That's why I'm not having to mess with the angles. Once I know FB now, I can plug it into here and get what FA is. So that's how I can get, that's how I actually can get both those forces. Okay. Now, did I have to make my axis here? No, I could have made it here. And then this wouldn't have provided a torque, and it would have been these guys rotating it this way versus this one rotating it the other way. Do you see how, if that's the axis, these are rotating it counterclockwise and FA is rotating it clockwise. So that'd be another way to do that. You could find FB first, and then you wouldn't even have to use this equation. Get rid of that equation. Just change your axes then and get the torque from FB then. Okay, these can get trickier if you have some angles involved. So let's say here's a beam going across. It's pivoted to the wall. There's a little pivot there, so it can move up and down. It can move up and down like that, but it's on an axis. And then there's a string that's holding the end of it, and then there's a weight that's 2 kilograms, and the beam itself is 2 kilograms. So they're both 2 kilograms. So the question is, what will be the tension in the rope? How much tension will there be in the rope? Okay, well, let's draw all the forces that are on the beam. So let's see, there's a force of gravity on the beam, 20 newtons. 2 kilograms, 20 newtons. There's a force of this string, this rope on the beam, and that's going to be 20 newtons as well. If there's 20 newtons pulling down, that rope should have a tension of 20 newtons. So this is 20 newtons as well. Okay, so I have two 20 newtons. I also have a rope, and ropes only pull, and they pull in the direction that they are that they're oriented. So I'm going to call that FT. And then we also have the force due to the pin. The pin is pushing maybe a little bit that way. That's the force of the pin in the X direction. There's a little pin in there, so it can pivot. And the reason I know it, there's got to be a force of the pin in the X direction, because something's got to negate the force from the rope pulling this way. So that's what's negating that. And then there is probably an upward force too. Can you imagine if I pulled this pin out? If I pulled the pin out, the whole thing would fly downward. And so there's a force upward, force of the pin in the Y direction. All right. So what I'm going to do now is I'm going to take this and I'm going to make sure that all the forces in the X and Y directions add up to 0, and all the torques add up to 0. Okay. Let's do the torques first. I'm going to have this be my axis. That's my axis, and here's why. I don't know the force from the pins. I don't know these forces. And if I don't know these forces, if I make my axis there, do you know how much torque this puts on the beam if my axis is right there? The answer is it doesn't put any torque, because the lever arm is 0. Same with this one. So let me show you my torque equation then. My torque equation is going to become the battle of the torques. Now, what are the battle of the torques? This is trying to rotate it. If that's my axis, that's trying to rotate it clockwise. This one's trying to rotate it clockwise. And this one is keeping it from doing that, so that's counterclockwise. See, if I pull here, it will go that way. But this string is pulling that way, and this weight is pulling that way. See? Clockwise, clockwise, counterclockwise. Okay, so let's do the battle of the torques then. Remember, I don't have to worry about these. They don't put any torques on. So 20 newtons times this length. Now this is a 1 meter beam, so times a half of a meter plus 20 newtons times a whole meter. That has to equal, now I don't take the entire force. The only part of this tension that matters is this part, the part that's perpendicular to the lever arm. If this is 30 degrees, then that's 30 degrees. So that would be Ft times the sine of 30 degrees. So it'd be Ft sine of 30 degrees. Now how far is this force from the axis? 1 meter. So at this point, I have only one unknown. The sine of 30 is a half. So apparently the force of tension, if you solve for this, this is 10 and 20, so that's 30 times 2, so it's 60 newtons. Because that sine of 30 is a half. So that's 60 newtons. That's what Ft is. 60 newtons. At this point, I will be able to get what the force of the pin is in the x and the y directions. Because the force of the pin in the x direction, there's only two forces in the x direction. There's this force and this force. And I know they cancel. So the force of the pin in the x direction is equal to 60 times the cosine, since that's 30, times the cosine of 30 degrees. So that's the force of the pin in the x direction. Now the force of the pin in the y direction, I can get that a few ways, but I think what I'll do is I'll just use all the y's got to add up to 0. So let's see how that works. The force of the pin in the y plus this force, which is 60 newtons times the sine of 30, that has to equal, in magnitude, 20 newtons plus 20 newtons. Notice these don't have lever arms because I'm just doing the force. So this is I use the net force in the x direction has to equal 0. And where did I get this from? Let me tell you where I got that from. That the net force in the y direction has to be 0. So that means the sine of 30 times 60 is that this is 30 newtons and this is 40 newtons. So that means the force of the pin in the y direction has to be 10 newtons. Sorry, it's so small, but that force of the pin in the y direction is 10 newtons, and the force of the pin in the x direction is 60 times the cosine of 30 degrees. All right, that's a static equilibrium problem. That's how you do that. You put all the forces on there, and you draw them where they are actually located. You choose an axis so that some of them disappear, so that there's no torques from some of them. Where you put the axis is very important. And then you just apply the equilibrium equations. All right. Hope this helped.